Okay, I'm going to show you how to use Phasor Addition to figure out what happens when you have more than two slits that are interfering to make an interference pattern. Also, I'm going to show you a few more things on coherence beyond what we discussed in the previous video. Okay, so what happens if you have more than two slits? What about a 3 or 4 or 5 slit pattern? How would you calculate what you're going to see? How would you figure out what you're going to see? I guess there's two different issues. How do you get intuition for what the pattern ought to look like, and then how do you actually calculate what the intensities in that pattern should be? Your book only does that for 2 slits. We're going to use something called a phasor diagram, Phasor Addition. You will probably see phasors again when you do Physics123. You'll analyze electrical circuits using phasors. But when you see phasors, what you should think is that this is exactly the same as complex exponentials. A phasor diagram is really just the complex plane, and we add things together in the complex plane. Alright, so let's consider 3 slits. So imagine, if you will, I have some wavefront coming in, I have some pseudo plane wave coming in, and it hits some foil that allows light to come through 3 slits. Alright? And these are supposed to be evenly spaced. So there's kind of 3 slits here, and the light can go through them. So we go to some screen a long distance away, go to some point on that screen, some angle theta, right? And we say, what intensity do I get up at some point on my screen at some angle theta to the direction of my laser beam coming in? Alright, well, what we do is we say, well, look, there's just 3 different waves that are contributing. Alright, so these 3 sources, these 3 slits, allow light to come through, and they expand, and when I get a long, long ways away, they come together on the screen at some point and they interfere. Alright, how big of an intensity am I going to get there? Well, what we can do is, just like we did with 2 slits, we said, well, let's assume our screen is so far away that effectively these lines going off at some angle are parallel, and then they're going to hit each other. You know, these parallel lines are going to meet at infinity on our screen a long ways away. And then we say, well, what's the phase? So I've got these light coming from these 2 slits, and I'm going to add them together, but I need to know the phase difference between these 2 contributions. And so what we did is we drew a little right triangle here. We said, well, if this is theta here, then this is theta here. If our slits are spaced by some distance d, let's say, then the difference in path length, this extra bit of path that this ray has to travel that this one doesn't, is just going to be equal to d sine theta. Alright, so we'll call that S, the path length difference. Alright? And then we say the phase shift between these 2 contributions is just going to be, well, for every wavelength of path difference, we get a 2 pi phase shift, so this is just 2 pi s over lambda, right? Well, if I have 3 slits, I just say, well, look, this one has to travel further than this one, so it's going to be shifted by this phase shift, but this one travels that much less. So you can kind of say, relative to 0, this one has, relative to my middle slit, this one has to travel a distance s, but this one travels a distance s shorter, and so they get phase shifted by, like, 2 pi s over lambda, where s, of course, is d sine theta. So if I were to draw, if I said each of these waves, instead of thinking of them as sine waves, if I thought of them as complex exponentials, right? Sort of some amplitude e to the I omega t plus some phi. Alright? The middle one will have some phase shift, but the top one will have a different phase shift, and the bottom one will have a different phase shift. So I could add them together. I could, at any moment in time, let's say at time t equals 0, the middle one, right, the bottom one has some phase shift, alright? The middle one has a phase, and the top one has a phase, alright? And so here we have this delta phi right here, and here we have the opposite delta phi, right? Negative delta phi. So we add them together, and we get our final amplitude. And then as time goes on, all of these rotate at the same rate, right? They're all oscillating at the same rate. And so what happens if I add these 3 together with my 3 slits, at some time they all add together, and as I let time go, they all add together at all times, and I get some oscillating wave. It goes up and down, and the amplitude is just the amplitude I get by adding those 3 vectors together in the complex plane. But let's say I go off axis a bit. So right now they're all added together, right? I said at some distance off axis, there's going to be a phase shift between this one and the middle one. And so I get something where I add them together. They do, all of the vectors in my complex plane are not all in the same direction. So I add them together and I get a length which is shorter than what I got when they were all in phase with each other. So if I go to some point off axis, they don't all add together and so in phase, and so I get a wave which is smaller in amplitude when I add them all together. If I go further off axis, those phases are going to grow, right? Once again, up here, the phase shift goes as d sine theta. So as theta gets bigger, the phase shift gets bigger. So if I go further off axis, the angle between these three vectors is going to get bigger, and I'm going to get less and less light until the three of them are all right on top of each other, right? I can have something where I have boom, boom, they kind of form an equilateral triangle, and they all cancel each other out, right? Then as I start to increase the angle even more, it starts to grow again. And eventually we'll get to a point where I have one this way, and one this way, and I'll be back to a maximum again, but it won't be as big as our original maximum. So let's just, to gain intuition, let's watch what happens if I sit at some point in time. So right now time is oscillating, and I'm looking at one point on the axis. So the phase angle between the three, the relative phases, is fixed, but time is changing. What if I fix time and just watch what happens as I increase the angle, as the phases between those three contributions change? So as you can see, they increase, boom, I hit a point where they cancel out, I get a submaximum, and eventually they're back into phase with each other again. So you see what's happening. This black line is a plot of intensity as a function of how far off axis we are. When we're right on axis, they all add together. But then as my theta increases, I get my phase shifts such that at some point they completely cancel out. Then I get a submaximum, and then it grows back up again. So using Phasor addition, I can sit down now, I can figure out what that phase shift is as a function of angle. We found that, right? And then I just add those three contributions together, then take the magnitude squared to find something proportional for the intensity, and I can tell you, I can get a formula for the intensity as a function of angle for my three slits. But also with Phasor addition, I can kind of develop some intuition, and I can see, oh look, I'm going to get this sub-maximum where they all add, 180 degrees out of phase with each other, but since there's three of them, they don't totally cancel out, right? And I get this sub-maximum down here, and I can explain that sub-maximum in terms of my Phasor diagram. So adding complex exponentials gives me the numerical, gives me the actual equation, but drawing our phasors can give us some intuition of what the interference pattern ought to look like. Now let's take a look at 5 slits. What if I had 5 slits? 1, 2, 3, 4, 5, all right? I go off at some angle, and I say, well look, again, just like my 2-slit pattern, this one has to travel further than this one, an amount s, which again is d sine theta, all right? This one gets a phase shift which is twice as big as that one, right? And this, right, because the phase between this one and this one, I draw that same right triangle, right? I do that again here, and I find that the phase between this one and this one is the same as the phase between this one and this one. So if I call this like phase 0, and this is delta phi, this one will have a phase shift of 2 delta phi, this one will have a phase shift of 3 delta phi, and this one will have a phase shift of 4 delta phi relative to this one, right? So if I look in my complex plane, right, if I'm on axis, all 5 of them add together in phase, and I just add together to make a nice big signal, right? And if I let time propagate, they all oscillate together. But if I move off axis, now they don't all add together, right? Each one, so I have, the top one, and then the next one, they each have a slightly different phase, so they don't add together completely constructively, and my net amplitude is smaller. Once again, if I freeze time now and move off axis and watch how these add together as a function of theta, I get something that looks like this. Boom, I hit a 0, there's a submaximum, there's a submaximum, there's a submaximum, and then it unwinds again. All right? And so once again, using my Phasor diagram, I can figure out intuitively what the interference pattern ought to look like just by figuring out what happens as I add these vectors together as the angle between them grows. All right? And then mathematically, I can do my complex analysis, right? I can figure out how long that blue amplitude is as a function of the position on my screen. And I can calculate the intensity pattern for a 5-slit pattern, a 6-slit, or 7. however many I want to do. Okay, so now just quickly, let's talk a little bit more about coherence. In the previous video, I mentioned that without coherence, it's hard to see interference. But it turns out there's two different types of coherence. There's what we call temporal coherence. And temporal coherence says, if I have, say, a laser, and it's making something that looks like a sine wave, and I watch it as a function of time, I look at that and I say, that's a sine wave. Since I know it's a sine wave and I know what its frequency is, if I know what it does for the first, 10, microseconds or nanoseconds or whatever, I'd be able to tell you what it'll be doing 200, at time t equals 200 microseconds or 200 nanoseconds, right? Whatever. So if it's a pure sine wave, I ought to be able to predict, from what it does at early times, what it will do at later times. Now, no laser is a pure sine wave, and so temporal coherence basically tells us how far out in time I can predict what's going to happen. And after one coherence time, I start to have enough uncertainty in what's going to happen. I'm not really sure if at some time I'm going to get a downward or an upward wavefront, right? So that's what temporal coherence is all about. And it turns out temporal coherence can also, we can write the coherence time, the time it takes for the light to randomly dephase and I can't predict what it's doing anymore. We can also take the coherence time and multiply by the speed of light and we get something known as the coherence length, which basically says, hey, if the light's coherent and I watch for a certain amount of time, how far in the future can I predict what's going to happen here? But you can also say, well, look, what I did here is going to propagate down here, and if at some time later I compare this, what's happening here, to what's happening here is what happened here at some time earlier. So I can get a coherence length, which is the coherence time times the speed of light, which basically tells me if I know what's happening here, how far downstream can I tell you what's happening here? If I know what's happening here, how far upstream can I predict what's happening there? All right? And temporal coherence, then the coherence time and the coherence length are both measures of the temporal coherence of my light. Now, what if my light doesn't have a lot of temporal coherence? What if instead of a laser beam I have a light bulb or a white LED that's putting out all kinds of sine waves? All right, well, if you don't have temporal coherence, it's hard to predict what's going to happen later in time or later in space. So when you make your interference pattern, what you have to think of is you have to think, well, I've got this white light that's making an interference pattern, but I can think of this white light as just a sum of different sine waves, right? Take the Fourier transform of it, it's all these different sine waves. All these different sine waves are going to all make interference patterns, and you may get something, all right, we talked about coherence time, coherent length. You may get something that looks like this, right? So right on axis, all the different colors are all going to add in phase, right? But as you start moving off axis, the contributions from the two slits start to get out of phase with each other. But the red light and the blue light get out of phase with each other at different rates. So what happens is right on axis, you have coherence, you have a constructive interference for all colors of light, and as you start to move off axis, all colors of light start to get out of phase with each other, but they all don't get out of phase at the same rate, right? The blue light starts to get out of phase faster, right? And so you get something which doesn't quite go all the way down to zero because when some colors of light are completely canceling, other colors aren't. All right, and then the level starts to come up again, and you get these fringes, and different colors get in and out of phase with each other. But after you go out very many fringes, you get to the point where one shade of red is a bright fringe, and one indistinguishably different shade of red is making a dark fringe, and your interference pattern just washes out. So whereas if I shot a laser in here, I'd have lots of red, or green or whatever fringes going out to 90 degrees. With white light, I get a white fringe, a black fringe, and then I start to get rainbows, and then it fades to gray. All right? So that's what happens if I don't have temporal coherence. If I don't have spatial coherence, what is spatial coherence? Well, spatial coherence, so temporal coherence said if I have my laser beam propagating this way, it says if I look at this point and I look at this point sometime later, how well can I predict what's going to happen at a later time? Or conversely, if I look here, how well can I determine what's going to happen here, right? That's temporal coherence. Spatial coherence says if I look at this point here and I look at it, so imagine I have a big laser beam here, all right? Here's my laser beam propagating. Spatial coherence says if I look at my beam here and I look at it here, how well does what happens here correlate with what happens here? Can I predict what's happening here based on what's happening here? So a laser beam basically emulates a point source. right? A laser beam, sometimes we call it a virtual point source. It's as if we have a spherical wave coming out. It's as if my laser beam was coming from an infinitely small point far, far away. So that what happens here is correlated with what happens here. But if I have a light bulb filament or an LED that's got some big emitter, light coming from this point of my LED and light coming from this point of my LED are not correlated. So I get this jumble of stuff, and they're always getting in and out of phase with each other. So if I look right here, that doesn't necessarily tell me what's happening here. Now when you make an interference pattern, what you have to do is you have to kind of say, well, let's imagine I get interference from this point, light coming from this point makes an interference pattern, light coming from this point makes an interference pattern, but they're not coherent with each other. So they're always getting in and out of phase with each other in random ways. And so I make, say maybe I have a point which makes an interference pattern that looks like this, but another point makes an interference pattern that looks like this, another point makes an interference pattern that looks like this, another one makes an interference pattern that looks like this, and eventually all those different points adding together incoherently so that they're not interfering in a regular way washes everything out, and I don't see interference. So if you take light from, a flashlight and put it through two slits, probably you won't see an interference pattern, because what happens is each point on the surface of that LED in your flashlight is making a different interference pattern that's offset from the others, and they all kind of wash each other out. So if I had like a white flashlight and I focused the light through a tiny, tiny pinhole, so it was like a spherical wave coming through, then I would get an interference pattern that looks like this, right? It's bright in the middle, but as I go off to the sides, it washes out as the different colors get, make different interference patterns. That's just spatial coherence. But now, what if my pinhole isn't small enough, and so it's not like a virtual point source, I have less spatial coherence? Then I get this figure right here that right from the get-go, I don't get very much interference. And if that pinhole is too big, I may not see any interference at all.